I'm the calculus professor, and today we'll be talking about physical applications of the integral. In problem number 47, we have a pool that's full of water that has a viewing window on one of its vertical walls. If the window is a square, half a meter on a side, with the lower edge of the window 1 meter from the bottom of the pool, find the fluid force on the window. So the very first thing that I want to do is let's just draw a picture of this situation. We have a side of a pool, and the side of this pool is 4 meters deep. Okay? So the pool is 4 meters deep, and then we have this window that's a square that's sitting 1 meter up from the bottom of the pool. So about a fourth of the way up, we have this window, and it's a little window. It's probably not that wide, just this little window sitting in there. And that window is 0.5 meters on each side. And we'd like to know, so this is 1 meter up to here. 1 meter to the bottom of the window, and then this window just has half a meter thickness. So really, how high is it from the top of the window to the top of the pool? How far would that be? Well, it's a meter here, another half meter here, so this would be like 2.5 meters to get to the top of the pool. Okay, so I think we fairly labeled this thing, and we can see what's going on. What I'm going to do is I've got to set up an axis. So what I'm going to do is I'm going to put the origin on the top of the pool where the water level is, and then say that positive y is down. If I do, then I can set up an equation for the fluid force, and it's going to be from some A to some B. Well, where does y start for the window, and where does y end? This is 0, that's not where we start. We don't start gathering force until we get down to this point, and that's at 2.5. And then we keep getting fluid force until we get to this point. This is 2.5 on my axis, this is 3 on my axis, so I keep getting fluid force until I get to 3. So in between 2.5 and 3 is where I'm gathering my fluid force. Okay, then I have my weight density comes next, and the weight density in this case, we're using water, so this is 9,800, times the length across the window at any point y. Well, this is a square, so the length across the window is just half a meter, or 0.5. So this is just 0.5 for the length, and then we need the depth. Well, since I set the origin at the top of the water, then the depth underneath that point is just y. So my depth is y dy. All right, let's rewrite this. I can multiply 0.5 times 9,800 to get 4,900 times the integral from 2.5 to 3 of y dy. I can take an antiderivative of that, and I get 4,900. And the antiderivative of y is y squared over 2, evaluated from 2.5 to 3. Plug things in, and I get 4,900 times, if I plug in 3, I get 9 halves. And then I plug in 2.5, and I get minus 2.5 squared over 2. Okay, and then I could go through simplifying this just a little bit. 2.5 is the same as 5 halves. So this is 4,900 times, I'm going to change this into eighths because it's going to help me in just a second. Changing this into eighths, that would be multiplied by 4, I get 36 eighths. And then this guy squared, this is 5 over 2, so I get 25 over 8. So we get 4,900 times, what would it be, 11 eighths? And that is going to be in newtons. So you could multiply that out and get the exact number of newtons of force on this little window.